Now that we understand a little bit what some of the pertinent issues are in fairness and why it really matters, let's look at some statistical tools. And this following section is taken pretty much verbatim from Corbett, Davis, and Goel's ICML 2019 tutorial that I strongly recommend that you watch in its entirety because it's super insightful. So let's start with a simple example. Let's say you're a police officer and you need to decide whether to stop a car because, well, there might be contraband in the vehicle. Okay. So what are the chances that there's contraband in the vehicle? And well, I guess we would all say, well, they look pretty safe, right? But this guy, yeah, well, maybe, maybe not. I mean, he's got his phone in his hand, so he's clearly not just as law-abiding person, or at least, whatever. Maybe the chances are a bit higher, whatever. How about some couple of retirees? Well, actually, they're also pretty safe, right? But those two, well, they might be very free-spirited and, think highly of things. So maybe there's a higher chance of finding some contraband. And this gentleman over here, yeah, clearly is up to no good. So he's fairly high on that overall risk scale. So if you were a police officer, and, if we look at the distribution of cars that he sees, and basically this curve is the number of cars or the frequency of cars that he would see at any given day with a certain chance that there's contraband. Well, he probably sees very few drunkards, thank goodness, and I guess most people are like this guy here. I'm definitely also guilty of that crime occasionally, but basically he needs to make a decision at some point, such as, well, maybe to, stop everybody out up here. Or maybe if he's very short-staffed, maybe he'll only arrest that many people. Or maybe if it's a, comprehensive test where they perform, our random breathalyzer testing, they will check everybody. Right? That's happened. Right? So the question as to where to draw this line, namely here, here, or here, depends on a lot of things. So for instance, if you are on 101, so the highway here, then they probably aren't going to do something of this form because it would just completely, create a significant traffic jam and would significantly disrupt a lot of business. I mean, on a country road in an afternoon, maybe you can do it. So this depends on, what the cost is of that decision. It depends on the resources that you have available. And at some point, you also may argue it depends on, what kind of a, country we want to live in, because, maybe not everybody appreciates being stopped daily by the police and being fleeced, even if that doesn't do any other damage, right? It's clearly unhealthy. So let's just abstract away from that. So here we have this risk distribution of, the likelihood of people possessing contraband. And we can clearly see that the majority of the people are, fairly low risk. And yeah. Now, maybe if we go to a different neighborhood, you might see something like this. So if you go to a bad neighborhood that has a reputation of being, highly trafficked, then the average risk is clearly higher. And so you can easily see that, therefore, if you were to, decide who to arrest, well, you'd be arresting more people, but also just that, this is a worse neighborhood. So maybe on a Friday night in a city, the chances of somebody, having something illegal in their car or maybe driving drunk is higher than on a Monday morning, At least one would hope so. Now, this is another case. In this case, actually, it turns out that, well, both have the same average risk. So it's actually been engineered in such a way that the red and the blue curve have the same average risk. However, it just so turns out that determining the risk for the red curve is a lot harder than for the blue curve. Okay. When might this happen? For instance, suppose you are on an army barracks and everybody wears a uniform, right? So you can no longer use any of their disheveled or not disheveled appearance to infer whether they are risky or not, or, you know, if everybody drives the same car because maybe they, you know, as said, drive an army truck, again, you can no longer use the car itself as a way to estimate whether somebody might possess contraband. So if, for instance, this were, you know, civilians versus maybe on an army basis, and let's assume that soldiers are just as law-abiding, or at least neither more nor less law-abiding than the rest of the population, then it could be much harder to make that determination for maybe somebody in uniform. Okay. And we'll see in a moment how that actually plays out when having to decide who to, you know, stop, or also to later on make some more, you know, impactful decisions on, you know, their lives. So, as already mentioned, those two groups carry contraband 30% of the time, so they're exactly, you know, the same in this regard. But if we decide that we will only stop people who have at least a 50% chance of carrying contraband, right? So this is, you know, at, you know, a specific cut point here, then it's very clear that the probability mass is much larger here. So the fraction of people being arrested that are blue is higher, right? But we are just stopping everybody who has at least a 50% chance of, you know, carrying contraband, and it just so happens that the blue curve has a much larger mass to the right of the 50% marker. So it also turns out that, you know, the searches of the blue group are more successful. So you now have this perverse situation where even though the blue and the red population are equally bad or good, more people in the blue group are being stopped, and even furthermore, more people in that blue group are, you know, being found out to be, you know, carrying contraband. So it just turns out that for the blue demographic, we have a much more discriminative tool to assess, you know, whether they carry contraband. Quick question, what would be the optimal distribution? Well, the optimal distribution would be one that looks like so, right? So you have a big spike here, and then you essentially have nothing, and then you have a small spike here. And in that case, pretty much no matter where you decide to make that cut, you can always fairly accurately assess whether they carry contraband or whether they don't. So a really good discriminator actually allows you to pick pretty much any cut here, and the outcome's pretty much going to be the same. Okay, it's not entirely the same because it's not exactly zero, but it's very clear that a green curve is going to lead to a situation where pretty much only the people carrying contraband will be stopped, and pretty much everybody who doesn't will be let through. So keep that in mind. Now, again, why is it the case that, you know, the blue group, you know, looks like they're the much more criminal one? Well, because it has a lot more obviously guilty people, so the hit rate is higher. It's not that the blue group is more criminal, but it's just easier to spot them. Now, what we could do, though, is we could say, well, you know, let's actually, because, hey, we've been so successful at, you know, arresting people in the blue group to, you know, so, you know, what are we going to do? Well, what we could do is we could just go and just, stop even more people in the blue group. So now, if you do that, what you're going to see is that, basically, so this is like picking a threshold of 45% for the blue group and 50% for the red group. And now you can ask yourself, is it now fair, right? Because if you were to do that, the probability of finding somebody who has contraband in both groups is the same. So the outcome, namely, are they actually, doing something illegal, is the same for blue and red who are being stopped. But really what's happening is that the blue group is basically being discriminated against, because you're now picking people who, if they were a part of the red group, they would have gotten away, and you're stopping them too. Yes, you're still catching more criminals, but actually the right thing in at least this context would probably be to, if you want to stop more people, to stop more people on either spectrum here in such a way that you overall, arrest more people. So the overall arrest rate would have gone up if you picked the green line versus what you're doing here with the blue one. So you're basically discriminating against the blue ones. So as said already, the hit rates are equal, but you're discriminating. So the outcome test doesn't find any discrimination even though there is one. Now, what's really going on here? Well, if you have a classifier, then there are lots of different ways how you can evaluate it, right? So, and let's take something as simple as binary classification, because that already contains an entire universe of problems in it. So you have positive and negative classes, and the classifier comes up with positive and negative labels. And so what you have is you can have, something that's of a positive class, where the classifier says it's positive, so that's a true positive. Likewise, negative is a true negative. And whenever the classifier makes a mistake, it's called a false positive or a false negative, respectively. So false positive is when the classifier says this is positive, but it's actually truly negative, and a false negative is just the other way around. Okay, so far so good. If we have a classifier, just a black box, this may work. It turns out, though, that usually we have a lot more, because our classifier usually will not just tell us, is it positive or negative, but it'll give us some score. So for instance, one of the models that we've looked at a lot in the past is a logistic regression classifier. And in this case, we're actually estimating a score function. So it's this function f of x. And if the value is large, we can be fairly confident that it's class 1, whereas if the value is very negative, we can be quite confident that it's class -1. And that now immediately, if you, think about that scale, right? Then, and here's 0, then if we were to make a decision here and label everything here as class -1 and label everything here as class 1, we would be getting fewer false positives, right? Because we are now using a classifier that's, more conservative. But we would be getting a lot more false negatives, because obviously in this region here, there might be a lot of positives that the classifier incorrectly that we've now incorrectly rejected. In other words, training a classifier is only step 1. Picking the right thresholds to decide, how to label things is another part. Now, there are a lot of diagnostics to assess how such a classifier works, and this is going to get us closer to the issue of, well, how do we know that our system is fair? So one thing, for instance, that you can do is you can look at the ROC curve. And the ROC curve, so receiver operator characteristic curve, this came from, essentially, radar in, during the Second World War. So what they did is they looked at, because they wanted to detect, German planes flying towards Britain, and they wanted to look at, how many false alerts do they get versus true, proper alerts. And they basically found a curve, right? And the thing is, obviously, whenever you see even just the tiniest speck, if you sound the alarm, you're not going to miss any attacking German plane. But the problem is your pilots and all your air defenses are going to get so tired that at some point they won't be able to fight anymore. On the other hand, if you are so conservative that you don't want to make any mistake, then it may be that you're going to miss half the attacks, and well, that's not so good either, right? So you need to find a meaningful trade-off. If you just do things at random, a random classifier is going to give us just a straight line between false positives and true positives. We can make this obviously better. That's what the classifier does. And the further we move in this direction, right, that's, how, that's basically a better model. So the optimal model would be one that looks like so, right? Where basically we get all the true positives without a single mistake. And then, well, okay, basically it doesn't ever really increase to, any meaningful false positives. So just to briefly refresh, the true positive rate is just the ratio between the number of positives that were identified as positive divided by the total number of positives, whereas the false positive rate is the one where it's the number of cases where, we decided that it's, positive, but it's actually negative, divided by the number of negatives. Right? You divide by the number of negatives there, because if you were to divide by the number of positives, then you might get the rate that could exceed 1 or be less than 1, depending on whether the classes are balanced, right? Anyway, so this is one metric, and it's very clear, what's better or what's worse. And a good classifier, will separate well. So let's look at another one, namely a precision recall curve. And precision and recall are actually, or can be expressed in terms of true positives and false positives. So precision is basically the ratio between true positives and the number of total observations labeled as positives. So basically that's true positives plus false positives. And if you want to have a system that has very high precision, so it doesn't make many mistakes in assigning a positive label, well, you will pick something very selective. So for instance, if you perform a Google search on fairness in machine learning, you would hope that the first few hits are going to be all highly topical. But then you keep on searching further because you want to learn more and more, and your search engine will eventually start returning results that are not just about fairness in machine learning, but maybe about fairness in sports or whatever. Recall, on the other hand, is the fraction of positives that you actually found. So let's say, for instance, that there's a gang of 6 criminals out there and you want to find them all, then you really want to have, perfect recall, right? Because you want to have basically, true positives divided by true positives plus false negatives. So basically you want to identify all the positives that are there. And if you only have a recall of, 4 out of 6, well, that means basically 2 criminals got away, and you probably don't want that, right? But it's, that trade-off. And again, it's up to you to decide where to make this cut. And every cut here in this context, or rather every point here on this curve, corresponds to a point on the previous curve, right? Might be here, might be there, whatever. But the point being, there are different ways how you can decide how to stratify things. And what you can also see is that different classifiers, or as we'll see also different demographics, different distributions, may have, or in general will have, different curves. Well, why? Because they are different, right? And so if you have multiple curves, the question is then, what's a good recipe where to cut those curves? And you can summarize a lot of the debate about fairness criteria into which of those diagrams should we pick and how should we cut. So let's just, recall the, risk distribution case. So in this case, well, we are conditioning on the value of z, which is p of y equals 1 given x, right? So that's like, if y equals 1 means has contraband, then this is basically what we do. Now, the risk function, right, the rho of z is just, integrating over, the, number of basically integrating over the distribution of x's. So this function, so basically this curve rho, right? Okay, sorry. This curve rho is given by integrating over all x's, for which, p of y equals 1 given x is z. So you integrate over possibly a very large domain. I mean, it's still density. At least if, we start with a density, we will typically end up with a density again. But it's now one-dimensional. Now, the nice thing is that once you have that risk function, you can find the true positives and the true negatives very easily. The true positives are essentially just the integral from that slice on, right? From z on, from a specific risk score on, up to, well, 1. Because those are the ones that are guaranteed to be risky. Those are the ones that are guaranteed to be safe. And you need to multiply by that risk score. So it's just t times rho of t dt. The true negatives are just the guys up here that survived, right? So there's, correspondingly, if you were to draw this, right? So for the blue curve, this will be the corresponding integral. These will be the true negatives, right? So this is therefore then 1 minus t times rho of t dt. Okay, so far so good. So, but this is just to put the risk distribution into context with what we saw before. And you can convert all those curves into each other. There are actually a lot more metrics. So for instance, there is sensitivity, specificity, accuracy, negative predictive value, precision. I don't always recall all those parts off the top of my head, and I also would probably go and consult Wikipedia to look up exactly what people mean when they talk about the specificity or sensitivity or the negative predictive value. And I suppose there's probably a positive predictive value as well, just because, well, you need that, right? So what I'm getting at is there are so many different metrics, and each of those metrics is reasonable, and it's been used in some context. And well, why do I think it's reasonable? Well, because otherwise it wouldn't have gotten a name and people wouldn't be using it. So just for reasons of practicality, that thing probably has a reasonable place. Okay, so now that we have all those metrics, well, what does it actually mean? Well, the thing is, we might want to match quality scores between different classes, let's say, whether it's, by race or by gender or by age or by location. But then now you can immediately ask a question like, is there the same false positive rate for arrests, right? Or do we have the same true positive rate for arrests, right? Sounds like it's almost the same, right? But it's not quite. Or do we have the same precision for arrests? Is there the same risk for arrests, right? Is there the same false negative rate for loan applications or, bail approvals or whatever? So in short, all of those metrics that I've shown you so far can lead to a question as to, are two or more, groups being treated equally based on that score? And it just so turns out that this is actually mission impossible. Now, there's a lot of really good theorems about that, but before we get into the math, I want to give you a quick picture proof. So let's take the ROC curve, right? So for instance, we could say that for a given true positive rate, right? And a given true positive rate basically just means a certain fraction of arrests should result in contraband found. So remember the example before where we said actually in this case, they need not be at the same risk. If I have, two demographics and I was just lazy to keep the words, good, better, and worse. But basically for a given true positive rate, this one here, I can clearly see that for different curves, I get different cut points. So I get different false positive rates. Now, a false positive rate means, well, that's the fraction of people that I end up stopping or arresting, thus, without them actually, carrying contraband. So if these were, three different demographics and maybe, those are the, folks in uniform, so you can't really tell whether they're good or bad because they wear a uniform. They all look the same, whereas, these are, highly individually, dressed people, so you can easily tell whether they're up to no good or not. Then it would be much harder to spot somebody there. So if we want to have the same, true positive rate, we'd have to arrest a lot more. On the other hand, if we end up, fixing the same false positive rate, we would suddenly find out that there are a lot more, so to say, criminals in the blue demographic rather than in the orange demographic or the green one. So it's very, very easy to draw strange conclusions. And those strange conclusions aren't due to the fact that people misunderstand statistics. It's just that once you pick a certain quality score and you say, well, I'm keeping one of them fixed and the same across different distributions and thus different, demographics, right? Then there is no guarantee whatsoever that the cut points end up in the same place for different curves. Okay. Now, what you could do is you could also simply say, well, I'm going to arrest, the same proportion of people, right? So I have, true positives plus false positives, constant. And that turns out that it's basically just, a diagonal line drawn. And again, if you do that, you're going to end up with different true and false positive rates for every one of them, but the sum of those is going to be the same. So again, well, something isn't quite right. We can play the same game for a precision recall curve, and I guess it's getting slightly repetitive because, again, what we'll see is that, for, a given set of criteria, you can neither do one nor the other properly. Okay, so this suggests that something is fundamentally broken if we try to compare multiple fairness criteria for a given threshold, right? And what we'll see in the next part of this lecture is that indeed it's a well-known fact, and this will require a little bit more mathematical tooling, that basically you can never really get all fairness criteria correct at the same time.